Imagine standing in your backyard with a giant drill. One so powerful that it can cut straight through rock, magma, and the core of the planet itself. You fire it up and start digging, going deeper and deeper past layers of soil, bedrock, and molten iron until, somehow, you've made it all the way through to the other side of the Earth. And then, because why not, you decide to jump in. What happens next? Do you plummet all the way to the other side like a cartoon character falling through a trapdoor? Do you get stuck somewhere in the middle, floating weightlessly? Or do you, melt before you even get halfway? Well, the answer depends on a few key factors. But before we get into the science of it, let's take a second to appreciate how insanely difficult it would be to dig a hole straight through the Earth in the first place. First off, let's talk about depth. The farthest we've ever dug is the Kola Superdeep borehole in Russia, which only goes down about 12.3 kilometers. That's less than 0.2% of the way through the Earth. And that hole took decades to drill. If we wanted to reach the center of the planet, we'd have to dig through about 6,371 kilometers of solid rock and molten metal. And to get all the way through to the other side, 12,742 kilometers. That's roughly the distance from New York to Sydney. But the real problem isn't just depth, it's heat and pressure. As you drill deeper, the temperature starts rising fast. The Earth's crust alone can reach over 1,000 degrees Celsius, which is 1,800 degrees Fahrenheit in some places. And once you hit the mantle, forget it. It can get up to 4,000 degrees Celsius, which is 7,200 degrees Fahrenheit. That's hot enough to melt iron. The inner core? About 5,500 degrees Celsius, which is 9,900 degrees Fahrenheit. Basically as hot as the surface of the sun. Oh, and the pressure? Yeah, that's another problem. At the center of the Earth, the pressure is a crushing 3.6 million times what we experience at sea level. That's like balancing 1 million elephants on your head. So, realistically, your tunnel would collapse long before you ever finish digging it. The intense heat would melt your drill, the walls would cave in, and even if you somehow lined it with an indestructible material, the pressure would turn that lining into a crumpled mess. But let's ignore all that for a moment and assume, somehow you do manage to drill a perfectly stable tunnel straight through the planet. And now you're standing at the edge, looking down into the void, about to jump in. What happens next? Well, the moment you leap, gravity takes over. First, things seem normal. You're in free fall, just like when you jump off a diving board. But unlike a regular fall, where you eventually hit the ground, there's no ground to stop you. You just keep accelerating, picking up speed as you plummet deeper into the Earth. Now, if this hole is frictionless, which it wouldn't be in real life, but let's pretend, you'd keep speeding up until you reach the center of the planet. By the time you get there, you'd be traveling at about 28,000 kilometers per hour, which is 17,400 miles per hour, roughly the speed of a spacecraft in orbit. But here's where things get weird. As you pass the center of the Earth, gravity starts pulling the other way, trying to slow you down. It's like when you throw a ball in the air. It speeds up on the way up, then slows down before falling back. So, as you continue past the core, your speed gradually decreases until, right as you reach the other side, you come to a perfect stop. And then, you fall right back down again. Yup, if there were no air resistance, this would be an endless back-and-forth motion, like a giant gravity-powered swing set. You'd keep oscillating from one side of the planet to the other, forever. Scientists actually have a name for this, a simple harmonic oscillator. And the total round trip? It would take about 42 minutes to go from one side of the Earth to the other. That's right, if you jumped in, you'd pop out on the other side just under 21 minutes later. And then you'd fall right back down and do it all over again. But here's the catch. In reality, air resistance exists. Even if you somehow built a tunnel that didn't collapse, it would still be full of air molecules, which means as soon as you start falling, drag would start slowing you down. You wouldn't be able to maintain that crazy 28,000 kilometers per hour speed. Eventually, friction would bring you to a stop somewhere near the center of the Earth. And without anything to push you along, you'd just float there, stuck in the middle of the planet in a weightless limbo. Well, until the heat cooks you alive. But let's say you solve that problem by vacuum sealing the tunnel and removing all the air. In this case, you actually would oscillate back and forth like a human pendulum until eventually Earth's gravity settled you into place at the center. Now, in case you're thinking, Okay, but what if we used some kind of high-tech magnetic system to keep the tunnel perfectly intact and friction-free? Congratulations, you've just reinvented a gravity train. Scientists have actually theorized about using this exact concept for superfast travel. If we could dig tunnels between cities that followed this curved gravity-assisted path, we could send passenger pods through them without needing any fuel. You'd simply drop into one side, fall under gravity's pull, and then let Earth's gravity slow you back down as you reach your destination. The best part? If done perfectly, this would work between any 2 points on Earth, not just straight through the center. Even if you drilled a tunnel from New York to Tokyo, you could make the trip in 42 minutes using nothing but gravity. So, is jumping into a hole through the Earth a good idea? No, it is not. But does the idea of a gravity-powered transportation system sound kinda cool? Absolutely. Now we just need to figure out how to dig 12,742 kilometers without, melting in the process. If you enjoyed this wild thought experiment, don't forget to like, subscribe, and hit that notification bell so you don't miss the next deep dive into absurd science. Thanks for watching, and I'll see you next time.